So oops. So can you see what's written on the slide on the sheet of paper?
Yes.
Yes. Okay, very good. So let us start the discussion of one of the central topics in the representation theory of quivers, so the so-called extensions. So actually, so we are used in linear algebra that the most fundamental object, which is somehow related to two representations of, well, two vector spaces, is the Hom space. So the space of homomorphisms from one space to another. And if we are working with the representations of a quiver, then definitely the Hom space is still there. So there's no issue about that. So you can also consider another space, which is also very fundamental. So it's called X Mn. Well, this is the space associated to two representations. So Mn are Q modules. And actually, there are two definitions. One is more computational, so meaning that this is the way how you can compute it. And another is more conceptual, so, well, it answers the question, what is the space responsible for? Okay, so let's start with the more computational, since it's somehow related to the projective resolutions we've studied last time. So recall that for Q module M, we have a short projective resolution. So P0 and P1 are projective representations, which can be constructed in a very concrete way. So now, given a Q module M, N, so one obtains the following sequence. So let me denote this map by F and this map by G. So I want the Hom spaces from M to N. To consider the map from this space to Hom 0n. So this map is nothing but G lower star. And actually, this is a very concrete map. So you just consider the composition of G with the homomorphism from M to N. And then we proceed with the map of lower star to Hom E1 N. So this is all fine. And the question is whether we can continue this sequence, and we can. So let us put here x mn 0. So we want some definition. So x mn is a vector space making the sequence above exact. So remark. So can we express somehow this X space in terms of P0, P1, F, and G? So can we write some formula saying what is this X? So we have the F, the maps FG, F lowest star, G lowest star, and home spaces, and we want the sequence written here to be exact. So we want this X space somehow to kind of close this sequence into exact one. So how to describe what is this X space?
The co-kernel of F star.
Right. So how to write it explicitly? So this is the quotient, yes, of sorry. So X M N is isomorphic to the quotient of home P1N modular the image of F star. Okay. So please raise your hand if this formula is clear for you. So for Dima it's clear, and what about other people? So Andrei, shall I comment on this formula somehow?
Sorry, I had problems with my connection. Now I'm connected just now.
I see. So I just said that this X space, it can be somehow, well, the definition is that the sequence written here is exact. And then in order to make it exact, this X space has to be isomorphic to the quotient of the home space P1N modulo the image of F star. And the formula just comes from the obvious observation that the map from home P1N to X MN should be surjective. So so this map is surjection, and the kernel of this map should be the image of F star. Hence, we have this description of X as a quotient space. Okay.
We use somehow that part of this sequence is exact, right?
Yeah, so the first of all, we can see that G lowest star has no kernel. So this is an embedding. Okay. Well, just because the map from P0 to M is a surjection, hence the G star has no kernel. And then we also need to check the exactness at the term home P0N, and this comes from the exactness of the short projective resolution. And now the obvious map from home P1N to X written as a quotient makes it surjective. And then the last thing is that the exactness at the term home P1N again follows from our form. Okay. So another remark is just a notation. The remark says that just want to say that XMN sometimes denoted by X1 MN. However, in principle, for some other examples of objects, there might be higher X spaces, but we don't need this here. And this is the only thing we need. So no higher X exists in the Quiver representation theory. So sometimes the X1 is written just by X. Okay, so this is the first definition, and in principle, it allows one to compute the X space if we have the explicit form of the projective representation. Now let us formulate the conceptual definition. So for that, we need to define an extension. So for two modules M and N, an exact sequence of the form 0 to N to E M. 0 is called an extension of M by M. Okay, so we have exact sequence. The middle term is something, and the right term is M, and the left term is N. So this is an extension. Or actually, the terminology, sometimes you would say that this extension of N by M, so whatever you prefer, maybe read even more natural, of N by M, because E contains N as a submodule and M is a quotient, so maybe it makes sense. So let me give one more definition. So two extensions 0 to N to E to M to 0 and 0 to N to E prime to M to 0. Please note that the N and M are the same, and the middle terms are in principle different, so are called equivalent if there exists a commutative diagram of Q modules of the form. So we have our first sequence, have our second sequence, and we have the identity map here. Have another identity map here, and we have something here, an isomorphism. So this is the form of our commutative diagram. So please note that the left and right hand isomorphisms are the identity maps, and the middle term is something. So the two extensions which can be somehow incorporated into such a diagram are called equivalent, and otherwise not. And this makes we are the position to make the definition. So X, so not to confuse the order. So maybe before, maybe in order to somehow make it more more readable, so let me introduce another letter, E, N. So this is just the set of pairwise non-isomorphic, non-equivalent classes of extension. So let us consider one example. So in order to see what's happening, so example, the example is as follows. So we take U to be Quiver on two vertices, and two arrows pointing out in one direction. Now let us take M to be as C as, so this is the vertex 1 and this is the vertex 2, and the M is S of 1. So this is a simple module which is concentrated at the first vertex, just one-dimensional thing, and N be S of 2. Okay, and now let us consider two extensions. So the first extension is like psi. So this is of the form 0 to M to N to E M 0, where E is of the form K A 1 0. So E is two-dimensional with one-dimensional spaces at each vertex. And so there is a sub-representation of this E isomorphic to S2, clearly, and the quotient is isomorphic to S of 1. So this is psi. And we consider eta, which is of the form n T prime M with very similar but a bit different T prime, is also two-dimensional, but the roles of zero and identity are interchanged. So now we wonder if is psi equivalent to that. So in other words, does there exist this commutative diagram here we have identity maps, and here an isomorphism. So what do you think? Are they equivalent or not?
I don't think so, because it seems to map E to E prime, we have to map it to a 0. The first K, we have to map it to a 0, the first vector space.
So you are saying
we
that
have two maps, from K to K and one from K to K, and
so we have K to K, yes. So so K to
K to K.
So I'm very sorry. I'll be back just in half a minute. Okay, just 1 second. So I'm very sorry. So can you see the screen?
Yeah.
Okay, so let's get back to the question. So we have k to k, and we have maybe let's write them.
So
K,
if we
k, and maybe no, it's not convenient. Sorry. So k, k, and then this is our e, and we have another k to k. So this is e and e prime. Yes. So
if we compare the upper arrows and since it should commute like the upper arrows, yeah, 1 and 0, then we see that at least one of the either phi or phi prime, say,
right, phi 1 and phi 2. Yeah.
One of them must be 0.
Yes.
Then we compare the lower arrows, and we
Yes.
see that both of them must be 0.
Why both?
Oh, okay. I suppose it's possible that only phi 1 is 0.
So I do agree with you that if you well, first of all, we want isomorphism, yes, of representations, yes. So phi 1 and phi 2 they have to be non-zero both, yes, otherwise this is not an isomorphism. And indeed, as you are saying, that if they are both non-isomorphic, they are both non-zero, then we can't have such an isomorphism, right? Okay.
Sorry, may I ask?
Sure.
Is this true that in general, if we have some map phi, it should be isomorphism just because it's included in such a diagram, or not?
So you mean if we have a homomorphism?
Yes, yes.
Then it has to be an isomorphism.
Yes.
Well, it's true by snake lemma.
Yeah. That's right. That's right. It's okay. Okay. So they are not equivalent, and actually, so we'll get back to this example soon, but let's keep this in mind. Okay, so there is one important thing about this definition. So far, this is just a set, and the claim is that there exists a natural structure of a Abelian group on the set E of Mn. So therefore, in other words, there is a way to add up two sequences, so two extensions. So let us present an explicit instruction. Okay, so we're given xi. And an eta. So these are two sequences. And then we want construct something which we call psi plus eta, and this is of the form 0 to n to e double prime m. So we need to construct e double prime, and we need to construct the maps from n to e double prime and from e double prime to m. So let me use some notations. So I put here u, and I put here v, and here I put u prime and v prime. Okay, and so first of all, let us define an auxiliary Q module F by the formula. So actually F sits in E plus E prime. So F consists of pairs x prime in E plus E prime, such that V of x equals V prime of x. Okay, so we take those pairs which are mapped to a single element in M. So note that the target spaces for V and V prime do coincide. Okay. So this is our F. And now in order to define E prime, so by definition, so E double prime is the quotient F modular the following pairs. So these are pairs of the form F U of n and minus U prime of n. We take F consists of pairs x prime modulo some condition, and we take a subspace consisting of pairs of this form for all n is n. Space. So an obvious observation is that if you take, so if you apply V to U of n, then you get 0. And if you apply V prime to U prime of n, you still get 0. So therefore, these pairs do belong to F. So it's okay. This is the definition of our space. However, we need mappings. So maybe I use another notation here. So this is U double prime and V double prime. So U double prime from n to E double prime is defined by the following formula. So n is mapped to U prime of n and u double prime of n. So you can see that indeed this is an element. Oops, what did I write? So this u and u prime. So this element belongs to our f, and we take actually the class of such an element. And we also need the double prime from e double prime to m. And the definition here works as x prime goes to v of x. So note that v of x coincides with v prime of x prime. Therefore, we could have written v prime of x prime. So this does not change the definition. Okay. So this is it. Of course, we have to check several things. And let's do this. So let me put gamma. So the sequence 0 to n to e double prime to m to 0 is well defined and exact. Okay. Good. So this is the statement. Let us prove it. Well, the condition of being a well-defined map is actually more or less obvious. Well, simply because the mappings are defined very explicitly. So first of all, as I said here, we have u of n and u prime of n, and if you apply v to both guys, you get 0, so there's no problem. And maybe I erase this. And downstairs, so say the maps n to e double prime and e double prime to m are well defined because v of u is 0 and v prime of u prime is okay, but let us show that psi plus eta is indeed exact. So what do we have to check? So first of all, let us show that n, so the kernel of the map n to e double prime is 0. So can you tell me why?
because if something lies in kernel,
Mhm.
It means that it lies in subspace of like, okay, we have u of n and u prime of n, and it should be like equal to u of n prime for some n prime minus u of, okay, yes, n tilde.
Right. And therefore,
We know that u is injective,
mhm.
so n tilde equal to n. But as well, u prime is injective, which means that n equal 0.
Yes, since u and u prime are both injected. So we conclude n equals 0. Okay. So this is the first thing to prove. And now the second, also more or less obvious thing. So let us show that the map E double prime to M is surjective. Well, can you explain me why? So I want to know that we want to understand that every element in M is covered by some pair in E double prime.
It is enough to take some preimages of some fixed element of M, or
Yeah, absolutely. So this is clear, since for any M in M, there exists an X in E such that V of X is M, and hence well, we can even write, so V of X is M and V prime of X, we might write better X from E and X prime from E prime, such that V of X in M is M and V prime of X is also M.
of X prime.
Yes, thank you. And hence, pair, well, a class of the pair XX prime maps to. So this is clear. So now let us show that the composition V double prime, U double prime is 0. So why is that? So we take the compositions of two maps. So we actually want to know a bit more, but this statement says that the kernel of V double prime is contained in the image of U. Oops, the image of U double prime is contained in the kernel of V double prime. So this is a half of the exactness, but this is an easier half.
It is just because both components of image under U prime live in images of U and U prime.
Yes, indeed. So we take V double prime of U double prime of some n. By definition, this is V double prime of the pair U of n, U prime of n, and this is 0. Okay, and the only non-trivial part is that the kernel of U double prime, V double prime, sorry, actually equals the image of U. How to prove this? So the claim is that if something sits in the kernel of V double prime, then we can cover it with some element from n. So what do we need to show actually? Yes, so so we take pair x prime, and so if we take V double prime of this, so by the very definition, this is V of x, or we can equally say V prime of x prime. And so this guy sits in the kernel of V double star. So it's equivalent. So let's say x prime equivalent to saying that V of x is 0, and the same calls for V prime of x prime. And now we want to say that this pair can be covered by the image of U prime. So it belongs to the image of U double prime. How to say this?
Well, both x and x prime are in the corresponding images.
Right. So we know that there exists an n such that u of n is x, and there exists an n prime such that u prime of n prime is x prime. But the problem is that these two elements are in principle different. Yes, so this is not exactly what we want.
Probably we should somehow use our quotient.
Absolutely.
They coincide in the quotient.
No, they don't coincide in the quotient, yes, because so n and n prime are elements in n, so therefore they are not inside the e double prime. But indeed, you are right. So we the elements x prime are defined modulo our f. So this is something we can use. So we have to cook up from two elements n and n prime one single element, which is mapped to the pair x prime, but we don't actually insist on the element x prime itself. We are happy with any elements from the same class modulo in this quotient. But none of the elements n and prime work in general. So what elements should we take?
I suppose that this is half of the sum.
Okay, let's check. So we take u double prime of n plus n prime over 2, right? So by definition, this is u of n plus and u prime n plus n prime over 2. And we actually want this element to be equal to x prime modulo the subspace we quotient by. So let us compare this. So this is x prime. So let me write them as u of n prime. So x. And then we have to add or subtract something. And what we have to add here is what? This is u of n minus n prime over 2. Am I right?
I think no. It should be this minus or n prime.
Yes. You are absolutely right. So oh no. So let's see. We take n. Yes. So this minus, right? So now it's better. And then the second component is u of u prime n minus n prime over 2. So I hope this is correct now. Is it? I think it is, right? And this is an element in F. Okay. And then we are done. So any questions about the construction? So just an outcome is that given two exact sequences, two extensions between M and N, so we are able to construct a new extension, which is denoted by psi plus eta. So, yes.
Maybe I don't know. Should we check somehow that it's this separation like does not depend on taking of classes of E and E prime?
Yes,
Or
in principle, yes. But let us see. So how does the definition work? So if we have two isomorphic, so I mean two isomorphic pairs of extensions. Yes. So say psi isomorphic to psi prime and eta isomorphic to eta prime. Then this means that the mappings in both so the mappings U and V in these pairs, they can be identified. So all the definitions given here, they are given in terms of maps between the modules. And since we are insisting on the commutativity of the diagrams when we are defining the equivalent classes, then all the definitions work just in the same manner for pairs of isomorphic extensions. So does this make sense?
you mean that if we have to say phi and phi1 for equivalences, and then for E2 primes, we can induce proper isomorphism from their sum.
Absolutely.
Okay.
Exactly. Okay. So let us make an example. So the example is as follows. So we take, as before, U to be a quiver with two vertices and two arrows. And the M is S1 and is S2. And the first extension is 0 to N to 0, 1, 0. And the second extension is 0 to N, K to K, 1, M, 0. So the maps U and V and U prime and V prime are clear. Yes, so these are embeddings and surjections. So the embedding is the second factor, second space is surjection, embedding surjection to the first, and this eta. And then the question is, what is psi plus eta? So just for us to feel how does this operation work. So maybe some suggestions or expectations. Or maybe just somebody can tell us right away. So what is this? Okay, so if not, yeah, yeah.
With two identities.
Yeah, so the natural guess is that this should be 0 to n to 3 to n 0, and here the two identity maps. Like this. Let's try to understand why. So the guess is very reasonable, yes, because in a sense we sum up the maps between the modules, but it's of course not exactly the strategy, but looks natural. So the first question is, what is our F? So recall that F is a subspace in E plus E prime. And this consists of pairs such that V of x equals V prime of x. So how does this Q module look like? So recall that V is here and V prime is here. So what is V after all? So can you tell me?
V is projection onto like first space.
Okay, yes, absolutely.
How to say it properly?
That's right. So then, how to then describe this F?
We have some of these two quivers and take subspace where what?
Some of these two representations, yes?
Yes, some of two representations, and we require that first components are equal.
So what are the dimensions of F?
3.
Yes, so this means that F consists of one-dimensional space at the first vertex, right? And a two-dimensional space second vertex. And so we have two maps. And what are the maps?
The first is 1, 0, pair of maps, 1, 0, and the second 0, 1.
So this one is just the identity, yes, and the just two different embeddings of K into K2. Okay, and now we have to quotient out F by the set of pairs X. Set of pairs U of n minus U prime of n prime. Oops, U prime of n. N from n. So n here is just S of 2. And U is an embedding onto the, just embedding to the second subspace, U and U prime are both embeddings. Yes, so how to? So the claim is that this is isomorphic to K 1, 1. Can somebody explain why?
We just identified two copies of K in the second term.
Mm-hmm. 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 Okay. So this is how it works. So now the expected theorem says that X mn is isomorphic to E of mn as abelian groups. Okay, so we have the definition of X via the projective resolution, and we have the definition via the set of non-equivalent pairs of actual extensions. And the claim is that the first definition is actually a way to compute the second one. So we are not going to give the complete proof, but let us at least define the isomorphism. Okay, so
May I ask a question?
sure.
Is it true that the zero element in that group is just direct sum?
Yeah, I should have said this. Thank you very much. I should have said this. So let us put as a definition a trivial extension is defined by 0 to n plus m to m to 0 with obviously defined maps. And then this trivial extension is indeed, so put this as a remark. So for any psi in EMN, psi plus trivial extension is equivalent to psi. Well, in principle, this is rather easy to see because well, how does the definition work? So we first consider our f, and well, we have x and x prime, but since e prime is trivial, so this is nothing but just saying that so v prime of x prime, just a second component. So we just say that v of x has to be mapped to, so we take the image of v of x, so e is our psi and e prime is our trivial extension, and this f capital F, something very simple, since v prime of x prime is just some given element. Yes, so the first component of x prime, this m plus n, so this is the first component of a prime. So therefore we just look at those x's which are mapped to a given element in M1. And then we take the quotient by the space where we take u of n, then minus u prime of n, and u prime of n is just n. So we take the quotient by the pairs u of n, comma n. So because u prime is just minus n, u prime is just a trivial embedding. And so it's easier somehow to, it allows to get rid of the component e prime. Well, of course, one better writes this, but just the claim is that if e prime is m plus n, then the two components, the two conditions we have, v of x equals v prime of x prime, and u of quotient out by u of n comma minus u prime of n, allows to get rid. So just writing that e separate this, that e double prime canonically isomorphic to just for e prime being m plus n. Okay.
And how to describe the inverse element in that group?
Inverse element. Let's see. So want something to sum up to this trivial extension, and you're asking whether there is some simple way to do this.
Maybe if we establish isomorphism from the theorem, we will prove existence of inverse element associativity, and maybe if we have explicit form of this isomorphism, we will be able to describe this inverse element, because it's easy to find it in XMN as in first definition. Or not, I don't know.
Let's see. Yeah, but the question is whether there is some easy way to do this. Just I want to put minuses somewhere in the mappings, but I don't know if it works literally. So I mean, if we have 0 to n to e to m to 0, whether maybe we can put take e to be maybe the same. No. Maybe e the same, and putting a minus somewhere. So u and v. maybe minus V. Would it work? I don't know.
By dimensional reasons, it's a bit strange.
What do you mean dimensional reasons?
I mean that if we take sum of this is, we should have m plus n. Maybe, okay.
No, this is a general
No,
pattern.
no.
So we take the dimensions of E, well, the dimensions of the central terms,
But
the sums of the dimensions n and m, right?
yes, sorry, it's so the same.
Yeah. So I would vote for this, but I'm not sure. Yeah, but it's a good question, actually. It's a good question.
Okay, thank you.
Okay. So now the proof. So let me give the constructions. So we have so we consider the projective resolution. Zero to maybe so 0 to P1 to P0. And we also have 0 to N E M 0. So assume that we are given xi in EMN, we are to define an element say alpha from home. So again, let me not mix the notation. So home P1n modulo the image of home P0n to home P1n. Okay. So this is our, by definition, this is our X domain. Okay. And how do we do this? So since P0 is projective, and the map E to M is surjective, so we have the following diagram. We repeat this. And so we go. And this is just the same. So we can consider the identity map. And now, if since P0 is projective, so we have a map from where to where? So M is just the same module, and then E to M is surjective. P0 is projective module. So what do we know?
We have
Yes.
a map from P0 to E.
Yes, absolutely. So let me denote this map. Somehow this is our U, it's our V. Let this be F, and this be G. And then we have the map H. So we have H such that this is a map from P to E with the property that G is the composition of V and H, right? Okay, and so recall that we need actually some map from P1 to N, and we claim that there exists a map alpha from P1 to N, which makes the above diagram commutative. Okay, so why? Actually, the reason is very simple. If indeed, so let us fix P1 on P1. So then what do we know about f of P1? So we know that if we apply G, this becomes 0. Because with this P1 to P0, PM is a projective resolution. And therefore, since G is VH, so VH F1 is also 0. Okay. Since the lower line in our diagram is exact, so there exists an element N such that U of N equals to HF of, and we define alpha of P1 to be this. Of course, several things to be checked. So first of all, so this is the class of N. So the class of N, to be precise. So of course, so this is the construction, but the actual theorem. So our theorem claims that this construction produces the desired isomorphism. Okay, and actually, well, we don't have time to prove this, and this is so your homework for the next time. So complete the proof. So in other words, we have to show that first of all, any homomorphism so alpha is a homomorphism from P1 to N. That any homomorphism can be obtained via some extension. Well, any homomorphism modular the image. And then the second is that only a trivial extension maps to the space which is quotient out as to this space. Okay, so I'll stop here. So any questions, comments, remarks?
Is it true that we could construct the alpha in that way? So we know that composition of F and H go to the image of U, so we can apply the projectivity of P1 to the pair N, NU and image of U.
Yes, yes, we can.
Okay.
But I have similar question, but as well we can use projectivity of P0 and construct map from P0 to N. But I don't understand if map constructed from P1 to N if it will be composition of this map from P0 to N with F.
So how you construct the map from P0 to N?
Just using projectivity of P0, we have map from P0 to E, H,
Yes.
and we have map from N to E, U.
But the map from N to E is not surjective.
Ah, okay, okay.
So it's not that simple. Yeah.
But well, then how can we then for P1?
Because we apply it not to E, but the image of U.
Ah, okay. So and then for P0, what is the problem that we are not in image of U?
Image
So
of
yeah.
H, maybe image of H doesn't contain an image of U, but image of FH does.
Okay, okay, I see.
Okay, further questions? So if not, let me save text and I stop sharing.